closed form expression of wideband FM. So in short, we do not have exact closed form expression which is generic, but we can use something which is the proxy, or we can say we would focus on single tone. And for the single tone, for the simple case of single tone also, again we would have some sort of a numerical solution. Just to rephrase numerical, that would mean that you would have some sort of an integration, and then based on that integration you have routines in various computing what you call tools such as Matlab or OR, and then you also have well documented and tabulated results. But either ways, so let us consider now that we have a message signal which is single tone. It has an amplitude of alpha, and then the message is cos omega mt, where omega m is the frequency in radians per second for the message signal. What we have is that we have to pass the message signal through an integrator. So if we pass it through an integrator, we would have the cos would turn to sine, and then the argument would be in the denominator, so we have alpha over omega m sine omega mt, right? And this thing is placed over here multiplied by a constant kf. Now again, we do not have an exact expression for gfm of t. So what we do is we use an alternate function, and that alternate function is coming from the Euler's identity. Specifically, if you have ej theta, then that would become cos theta plus j sine theta. But if you take the real part of it, then you would get cos theta. Thus, j sine term would cancel out. So from that, if we just simply say that gfm of t is simply a real part of gfm hat of t, right? So they are equivalent. So we are not approximating the message signal, we are just constructing a more generic form in terms of exponential, and then we'll take a real part and then we'll come back to the intended expression for frequency modulated signal, right? So we have a, e, j, and the argument of this thing, which is omega ct kf alpha over omega m sine omega mt. So from the property of exponential, that is e a plus b, we have e a times e b. So we have e j omega ct times e j kf alpha over omega m sine omega mt. Previously in narrowband we have a similar expression, and we used Taylor series, but in that time it was converging, such that the higher values in which you have kf square a square, they were actually, this whole thing were converging, and the values were becoming smaller and smaller as you increase the order. But right now this is not the situation. This can be a big value, and if it is greater than 1, the square of it and the cube of it actually would grow exponentially. So we cannot cancel out the higher order terms. So that's why we cannot use the series expansion for this particular problem. But what we can do is, we know that this exponential function ejkf alpha over omega m sine omega mt, this exponential function is a periodic function. So if it is a periodic function, this omega m, we can find the time period tm, which is 2 pi by omega m. So if it is a periodic function, we can express it in terms of exponential Fourier series, which is expressed over here, that n minus infinity to infinity, the summation of weighted exponentials for particular harmonic. So omega m is the fundamental harmonic, then this n identifies the nth harmonic, right, in radians per second, right? And this dn is the coefficient or the weight that we are going to multiply with the exponential. Dn is simply 1 over time period 1 over tm, the function or the given message signal, which in our case is this one, times e, j, and omega mt, a simple straightforward definition of an exponential Fourier series. So this expression is basically analysis. So you can go back to chapter 2 of the textbook, and you would find that expression over there, and also in signals and systems, right? So if we plug this value over here, so we have this this integration. Now to simplify this integration, we apply a change in variable approach, and for that we are interested in getting a single variable inside the argument of sine function, and that variable is we term it as x. So we say that when x is equal to omega mt, right? So when x is equal to omega mt, so we would have sine of x. But if you get this definition, then a number of things would change, which we have expressed over here. So if x is equal to omega mt, so this dt would change to dx. That would mean if you have dx by dt, so if you differentiate this, so we have dx by dt, so that would become simply omega mt, right? So if you differentiate this t would cancel and you would simply have omega m. So this dx is equivalent to omega m, and dt would go over there. So dx is equal to omega m dt, right? So we can change dt to dx, that is dt is equal to dx by omega m, right? So this omega m would cancel with this omega m, right? Actually it's expressed over here, right? So we would have a simpler expression. Another thing is regarding the limits of integration, the lower limit and upper limit. Since now our new variable x is equivalent to omega m into t, so this original t would be multiplied with omega m. So if you multiply this with omega m, this omega m would cancel with this omega m. Simply on the positive side, this omega m would cancel with this omega m. So you would have an integration which is from minus pi to pi, minus pi to pi. So we would have ejkf alpha over omega m sine of x e minus j n omega m t, again reappearing over here. So this will become x, which we have expressed over here, and then dt would change to dx over here. And moreover, we have used the definition of modulation index, which is kf a over omega m. So this variable is now expressed as beta. So this is again an integration. Now the important point is that we do not have a closed form expression for this coefficient, or in short, we cannot solve this integration. So if we cannot solve this integrations, what is the way forward? The way forward is actually, this is basically a definition of a Bessel function. So this is simply, this whole thing is a Bessel function. So the whole discussion so far of the closed form expression is that we are modeling the expressions so that we get into some kind of a function for which we have certain value of some tabulated results. So this kind of an integration expression has numeric values in terms of integrations, right? So this is simply a Bessel function of the first kind, having order n, and in the argument we have beta, which is the modulation index, right? So another thing to notice herein is that we have two variables. The first variable is beta, that would play a role in the outcome of this integration, and that is our modulation index. Second variable is the harmonic, which harmonic we are dealing with, that is n, order n, right? Order of the Bessel function. So the harmonic and the beta are going to determine the actual or the numeric value of this function. Another thing is, if the solution is there, if a numerical solution is there for this function, so that solution would subsume x variable, because the integration variable disappears in the result. So if you solve this, if any integration is solved, the value of the variable by which you are integrating, that is no more than the expression. So this function jn of beta is basically dependent on the harmonic and the modulation index, right? So this whole thing we have expressed in terms of Bessel function. Now there are some very interesting aspects of this Bessel function. The first aspect is that it is what you call anti-symmetric on odd harmonics or odd values of n, and it is even at even values of n. So this means that if you have j1 of beta, right, so j minus n would be if you put n equal to 1, so this n will be 1, so minus 1 raised to power 1 is simply minus 1. So j minus 1 of beta is equal to minus j n of beta. But at the same time, if you put n equal to 2, so j minus 2, so minus 1 raised to power 2 is simply 1, so this would be cancelled, and this j2 of beta, so that means j minus 2 of beta is equal to j2 of beta, but j minus 1 of beta is equal to minus j1 of beta. Another thing is, actually from this we can further extend it, that if you take the absolute value of this and if you take the absolute value of this, so then that would mean for the absolute values we can get rid of this term, because in the absolute we are just getting the positive value, so we can just ignore this aspect. Then j minus n of beta is equal to j n of beta. So equation number 2, so this is equation number 1, this is equation number 2. So we have now expression of dn, which is in terms of Bessel function, that is expressed over here, jn of beta. So we have jn of beta times exponential, and then if you put this 2 in 1, this expression, this actually was expressed in terms of exponential Fourier series, but for that we have the value of dn, which is in terms of Bessel function. So if you put all of this in expression 1, so we'd have a exponential of j omega ct, and for this we have a summation dn is in terms of a Bessel function times ej and omega mt, and all of this is basically expressed over here. A ej omega ct dn changes to jn of beta Bessel function times ej and omega mt, right? And then we can express this, we can take it inside the summation, and if we take it inside the summation, we have exponential of a times exponential of b, which we can combine in terms of a single exponential, which is exponential of j a plus b, so omega c plus n omega m, so n omega m, right? So this exponential and this exponential are combined over here in this equality, and we have a n minus infinity to infinity j n of beta ej omega c and omega mt. All of this was basically for specific for g hat fm of t, but if you take the real value, so we will get back the original g fm of t. If you take the real value of this one, so this function can be expressed in terms of cos theta plus j sine theta, but if you take the real value only, we would be left with the cos function, right? And this is an expression which is in terms of Bessel function. It looks closed form, but we have not used a trigonometric function like an exponential function or a cos or a sine, but we have used a more advanced Bessel function. Nevertheless, we have numeric values of this Bessel function that we can utilize. Before we move on, let's talk about again the power of this signal. What would be the power? So if you take the power of this signal, we can say this will become time period t naught and g fm square of t dt, so 1 by t naught. But since this is a cos function, if we square it, as I mentioned previously, it will become 1 by 2 plus 1 by 2 cos 2 theta. So eventually if you take the power of this function, so you would have a square by 2 summation n equal to minus infinity to infinity j n square of beta, right? And this expression is the power of GFM. But the Bessel function has also this property that if you take the square of j n square of beta and then you sum all of those Bessel functions, then that would be equivalent to 1, right? So we would have simply a square by 2, right? We will be deliberating on some of the aspects of Bessel function, how it can be used in frequency modulation, and how we can analyze the systems. So we'll start with a small simulation in Matlab to plot the Bessel function. So this over here is Jn of beta. So on the y-axis we have Jn of beta, and on the x-axis we have beta, right? And in Matlab you can use Bessel J to identify that you are talking about the Bessel function of the first kind. Then 0 to 6 is the value of n, which is over here, right? And x I have simply used to reflect on beta. So we have a set of curves, a number of curves, and the range is that we have a 1 here, 0 0.5, 0 minus 0 0.5, right? So for this, the first one is, the blue one is J1, then the red one is J2 of beta, J3, J4, J5, J6, and so on. So I have used from 0 to 6. So 0, 1, 2, 3, 4, 5, 6. Right. So these set of lines identify different values of different orders of the Bessel function. Right. The first one, the blue one, is representing the DC value. That is when our n is equal to 0. Right. This is representing when our n is equal to 1, the fundamental harmonic, and the second harmonic, and the third harmonic, and so on, right? So let us see how we can use this Bessel function. Specifically, consider first the narrowband FM. For this figure, I have taken a portion of it, the initial portion of it, which I have replotted here. This is Jn of beta from 0 until 2, but we know that for narrowband FM, the value of beta is less than 0.3, right? Let us take this value, which is 0.25. So that justifies the selection. Since it's less than 0.3, so we can say it's narrowband FM. And from our previous discussion, we have said that JFM of t is equal to AC, the summation of the Bessel functions and the cos function, right? So at this value of beta, we have a beta here. If you pull this up and cross this point, so at this point all the other orders are 0, but we have blue line which is approximately equal to 1, and then we have this red line. So this is 0.25, so that means this would become 0.125. Over here we have 0.25. So at beta equal to 0.25, we would have the DC value which is 1. So this is basically representing our original carrier when we set n equal to 0. So if we set n equal to 0, so we have AC cos omega ct. So why is it so? Because this AC is coming from here. So when our n is equal to 0, so j is 0 of beta. So j 0 of 0.25 is simply almost equal to 1, right? So this will become 1. So that will cancel out, right? And this n is 0. Why is 0? Because for this function we are saying that n is equal to 0. For this we are saying n is equal to 1, n 2 3 4. So n 2 3 4 are all 0, but we have n equal to 0 and n equal to 1, which is blue and red respectively. So if n is equal to 0, so that means we would simply have cos omega c t. So this whole thing is basically governed from this blue line at n equal to 0, which is giving us this value. So next is the red line when your n is equal to 1. So when your n is equal to 1, it is almost showing a linear behavior initially, right? So since it's showing a linear behavior, note that at 0.25, Jn of beta is basically giving you half the value of 0.25. So that means in this range, this is equal to beta by 2. If beta is 0.25, Jn of beta is beta by 2, that is 0.125. So this approximation holds until 0.3, but not later on, since you can see that the slope is decreasing actually. So this is linear until 0.3, and with that linearity we can claim that in that linear region, this x-axis, if this is beta, then y-axis is beta by 2. So when your n is equal to 1, which is over here, so when your n is equal to 1, j1 of beta is simply equal to beta by 2, so beta by 2, right? And AC would just it can be reproduced as it is. And next, your n is 1, so we will have cos omega c plus omega m. Now we have mentioned previously that the Bessel function follows anti-symmetry on odd values of n. So if n is equal to 1, for j minus 1 you would have minus 1 of jn. So this would mean that j of minus 1 of beta is the minus value of beta by 2. So you have minus beta by 2, and again this n is, since this is minus 1, so you would have omega c minus omega m, so cos omega c minus omega m into t, right? So this is actually an exact expression that we previously found out in our previous lecture on narrowband FM, but we can also derive this using the Bessel function. Now the things become actually quite interesting when we are dealing with wideband FM. That was the whole point. So all of these values can be tabulated in terms of this given table. The column and the rows are representing the values of beta, so 0, 0 0.2, 0 0.4 until 6, and on the columns we have the Bessel function of first kind and of order n. So over here it's 0, 1, 2, 3, 4, 5, 6 until 9, right? So these are available in literature. You can just search it on a search engine and you would find this kind of a table. So what this represents is that for a given value of beta, say 2, and for the first kind j1 of beta, so j1 of beta at beta equal to 2 would be 0.58. So this means that, so 2 and this red one is around 0.58. So this point is approximately 0.58. So all of this is basically tabulated in this table. Okay, so before we move on, there's something that I mentioned which is called 1% tolerance. So that means that it should be 0.01. That means the percentage of power should be greater than this one. Power should be greater than this one. So if we have this 0.01, so we will not consider this value, but we would consider this one. So that means the maximum power is available in first harmonic. This is the DC value, the first harmonic and the second harmonic, and in the third harmonic we don't have a lot of value at 0.8. So until here, this is our n max, the maximum point that we would consider. We would not consider 0.01. So over here we have used 0.02 because it's greater than 0.01. So anything which is greater than 0.01, that would be considered. How it would be considered, I would deliberate on that in a while. Furthermore, this whole table is just simplified in terms of some key points. That is modulation index beta, we have 0.1, 0.3, 0.5, 1, 2, 5, 10, 20, 30, right? And then number of significant side frequencies, 2 n max, right? This was n max. Over here we are saying 2 n max, 2 times that. Actually this is not n max, the order corresponding to the value which is just greater than 0.01, right? So this 2 is the value which is just greater than 0.01, so this is our n max. So over here it's mentioning that 2 n max. So for these modulation indexes we have these values of 2 n max. This whole thing we have plotted in terms of a universal curve, so it's a very important plot. The whole of this is basically plotted here. So in this universal plot we have a modulation index which is beta, and on the y-axis we have a normalized bandwidth that we have referred to as bt delta f. Let us talk about the value, for example 0.1. So it says that it has 2 nmax. So from this table we can express that the bandwidth bt of the transmitted signal or of the frequency modulated signal is equal to 2n max times the bandwidth of the message signal. This 2n max is simply 2, so 2 times bm. That is the bandwidth of the message signal, which is in agreement with our narrowband FM discussion. So if we're using this plot, universal plot, so it's starting at 0.1. So at 0.1 we have a value of 20. So from here we can say that bt by delta f, this is equivalent to 20 for beta equal to 0.1, or simply we can say bt is equal to 20 delta f. Remember, delta f is simply the deviation in frequency, so this is 20 times beta times bandwidth of the message signal, where beta is equal to delta f by bm, right? So we have 20 times beta, we have considered 0.1 as done here, so 0.1 times bm, and hence this is equal to simply 2 bm. So the point of doing this exercise is that this and this are actually the same thing, so either you can use this table or you can use this curve to get the bandwidth. And also not all values are available here, so you may need to go and fetch the value from here. So we don't have a value of 0.1 here, we have a value of 0.2. So let's just hold that thought for a minute of how to use this table, right? So let's pick another value in which we have a value over here, here, and in that table. So let's pick the value of 2, which we have done previously. Let's pick this value 2. So this is available in this table, and it is available over here, and definitely all the values of betas are available over here. So let's start with the value of 2 from the simpler table, this, and this corresponds to 2 n max equal to 8. So from, we can express this as simplified table. So from the simplified table we have transmission bandwidth bt, which is equal to 2n max times the bandwidth of message signal bm. So 2n max is over here 8, so we can say this is equivalent to 8 bm. Simplified table. Let's check this with respect to the extended table. So this is 2n max bm. So in the extended table, which is over here, the value which is greater than 0.01 is 0.03. It is this value, and the order of this one is J4 of beta, right? So this value would be 4 to 4 of bm. So this will become 8 bm. So this is in agreement with our simplified table. Now let us again look into the universal curve. So if we are interested in beta equal to 2, so this would almost be equal to approximately equal to 4. So if it is approximately equal to 4, so we can say from the curve the transmission bandwidth, normalized transmission bandwidth bt by delta f is approximately equal to 4. Yep. And that means bt is equal to 4 delta f, or 4 times beta times bandwidth of the message signal, or 4 times bandwidth, and the beta we have expressed as 2, the modulation index we have selected as 2, so this will be simply 8 bm. So in agreement, all of the three, the two tables and the universal curve are in agreement with each other. Now compare this with the Carson rule that we have discussed previously. And in the Carson rule, we have expressed that the bandwidth is 2 bm beta plus 1, right? So that means this is 2 bm beta we have selected as 2 plus 1, and this is equivalent to 2 plus 1 is 3 into 2, 6 bm. Now over here we have a difference. From the Carson's rule, we have the bandwidth which is equal to 6 bm, but from the two tables and from the curve we have a bandwidth which is 8 bm. So which one is correct? Actually, both are correct in a way. This is some sort of a lower bound, and this is some sort of an upper bound, and the actual bandwidth of an FM is between the Carson's rule and the function that we obtain based on the and the result that we obtain based on the Bessel function. So the actual bandwidth is actually in between, so it may be around 7 bm, right? So just one quick reflection, why it is underestimating Carson rule, why is it underestimating? Remember when we did the visualization previously, in the visualization we had 2 delta f plus 2 bm, but as per Carson he said this is overestimating, so he got rid of this value 2, right? So he got 2 times delta f plus bm. So in getting rid of this 2, he is actually underestimating it. This was overestimating by a very large extent. This is underestimating to a small extent, right? So that is why in our recent result of Carson we have some sort of an underestimation of 6 bm, which is less than. So an interesting point over here is that if the value of beta is quite large, so if you have 20, right, so this will be around 2.5 because this is 3. So for this kind of a scenario, when your beta is equal to 20, if beta is equal to 20, right, for that bt by delta f would be equivalent to 2.5, and that would mean that bt is equal to 2.5 times beta times bm coming from delta f, right? So this is 2.5 times 20 beta m, and this is simply 50 beta m. So as the value of this beta function increases, so you would have, if it is 30 or 40 and so on, so you would actually be getting around, so it would be, if the value of beta increases, so you would have something like beta, and the transmit bandwidth would be actually equivalent to 2 times delta f. So for this I would suggest you to do all this analysis wherever possible. You have 20 here, so you can definitely use this table, you can use this curve. Actually, in fact, I have used it, but you would not be able to use based on this one. So maybe you can plot it from a Matlab, and the function is already there, and you can find the value from the Bessel function in the Matlab to eventually get it.